All right, good morning, everybody. So before we finish up the last few slides we had from last time and before we begin our inverted lecture for the day, let's go through and refresh on our functional groups. So I'm going to draw a functional group or molecule that contains a functional group, and you all tell me what the functional group is, okay? So I'm going to start off with something like this. That's an ether, right? That is an ester. Sulfide. Yep. That's a tertiary amide. Amide would be fine here. An amine. All right, so that's pretty good. Haloalkane, that would be this. This is an acid chloride. It's on the list that we covered on the list, but it's at the bottom. It's the one that I said that was really, really reactive. Okay? So I'm hearing some good progress on the functional groups. That's good. So keep it up. Again, you're going to have to review these quite frequently because these have to be able to come to you fairly rapidly. You have to be able to see them by sight. You have to be able to, if I asked you to draw a tertiary amide, you need to be able to draw one. Okay, so you've got to know it both ways, so to speak. All right. So how would we distinguish between an alcohol and a carboxylic acid? Okay, but how would we, that's true, there's the difference is the carbonyl group. How would we distinguish between the two? If I gave you the alcohol and you didn't know it, and I gave you the carboxylic acid and you didn't know it, how would you prove to me which molecule you had, which functional group you had? But how would you prove that? IR, right? Yeah, so we can distinguish between functional groups using IR spectroscopy, right? That's what we were talking about the other day. What would we be looking for in the alcohol in terms of the IR spectrum?
Like a large one.
Yeah, we would be looking around 3,300-ish, right? And we would hope to see something that looks kind of like that, like a parabola. What would we be looking for the carboxylic acid? We'd be looking for the carbonyl. Where would we be looking for that at?
1,700.
Somewhere around 1,700-ish, we'd see a sharp peak, right? And what else would we have to see? Because there's a lot of things that have the carbonyl. We'd also be looking for the OH. And so around, again, that 3,300, we would see a broad. Carboxylic acids are more broad. They're not as parabolic, if you will. They're a little messier looking, okay? But you have to have both of these present for it to be a carboxylic acid. Okay, so we're looking for these signatures in the IR spectrum to tell us which compound we have, or molecule we have. So, this is the one we finished up on Wednesday. Let's see if we can see it a little bit better. Right, where do we start? We look at 1,500 and we ignore everything to the right. Very good. And we move out how much? 500. And that's what region? So I see a nice strong absorption in the sp2 region. Based on that information alone, I can eliminate something. What can I eliminate? I can eliminate A. Okay? One of the reasons why I do stick with multiple choice exams, other than the fact that you're going to be taking a multiple choice final exam at the end of 256 that's standardized, is because this is, in a lot of ways, how doctors think about things. And many of you want to go to medical school. And believe it or not, more times than not, you will not really know what's causing the ailment of your patient. What you will know is what it's not. That's why it's called practicing medicine. It is an experiment every time you see a patient. Okay? You look at the symptoms and you eliminate things that you think it can't be. Then you prescribe a course of treatment, which is an experiment to see if at least it supports your hypothesis. Okay? Doctors don't talk about hypotheses and things like that, but it's really the same thing. So being able to eliminate what things are not is sometimes just as important as being able to determine exactly what it is. Okay? So being able to eliminate is very, very important. So we can eliminate A. Can't be A because there's no sp2 hybridized anything, right? And so it can't have an absorption there. But it can either be C, B, or D. Which one would be your next one that you would eliminate readily? I would eliminate D right off the bat because I don't see a broad, nasty-looking OH stretch for carboxylic acid. So I've eliminated A, I've eliminated D, I just went to B and C. That's a 50-50 odds. Chances are you're going to be able to find an antibiotic that can treat 50-50 for your patient. They'll probably go away happy, okay? So now we've got C and we've got B. Which one's the correct answer? B, right? If we were looking at C, we should be able to see two stretches for these NHs, and there's nothing in that region for the NH stretches. And so it's just sp3 hybridized CHs and a carbonyl. So the only molecule that comes close to that is this one. Okay, very good. Let's look at this one. Where do we start? Pardon?
Eliminate D.
Pardon?
Eliminate D.
No. Where do we start? 1500, right? We don't start by just eliminating B, all right? We start at 1500, we ignore everything to the right. And then we draw in our sections. So there's the sp2 region, there's the sp region, and there's the hydrogen region, right? So what do I know just by looking at that? Pardon? There is no OH. Okay, so we can probably eliminate B. All right. But we can also eliminate B for another reason. Not just the OH, but the absence of what? Of a pi bond, of a carbon-carbon double bond, or something that would give rise to an absorption in the sp2 region. All right. So we can eliminate B. What else can we eliminate?
C.
Why can we eliminate C right off the bat?
This stretch isn't big enough for a carbon-carbon triple bond, is it?
Which one?
2500.
Right here? It might be. Notice a lot of these other ones have carbon-carbon triple bonds too, right? There's something in the sp region. We know that, right? What other one doesn't have anything in the sp region? D. B doesn't have an OH, and D doesn't have an sp. So we can eliminate B and D. That leaves us with A and C. Which one's the correct answer?
Is it C?
Oh, it's A. Now wait a second. Something in the sp2 region, there's something in the sp region, right? Why can't it be C? What am I using to distinguish A from C? The CH. Remember, the hydrogens that are attached to things like alkenes and alkynes will be shifted a little further this way. So we should have seen the sp3 hydrogens, if it was C, but we also should have seen another peak just to the left of that, and we don't see that. So I can eliminate this alkyne because I don't see that CH stretch. And this one doesn't have a CH, right? So this structure better matches that spectrum than does C. All right, how about this one? Got to be C, and it's got to be CY. The OH stretch. Very telling. Very telling, right? So it's the only alcohol up there. Got to be it. Plus, if you look, there's 1,500. There's really nothing between 1,500 and 2,000. That would have eliminated this, this, and this. You could have also used that rationale. Okay, both of those pieces of data are consistent with that particular structure. How about question number 4? Which of these structures is consistent with the IR spectrum? It is B. We have a carboxylic acid. What you'll notice is we have a nice strong absorption between 1,500 and 2,000, which is the carbonyl. But notice how this stretch is really broad and kind of ugly. That's the OH in a carboxylic acid. And it actually starts to overlap all of these CHs, and that's why it starts to look ugly. Okay? So we know that that has to be the carboxylic acid. All right, that finished up what we were doing the last period. Get in your groups. We'll go ahead and hand out the inverted lecture. I did post a Solutions to Inverted Lecture 1 on YouTube to kind of give you a better idea of how to answer these types of questions. Just to let everybody know, I've had a few questions about the grade on that. Don't worry about the grade. You all did about as expected on the first one, so not bad.